The year is 1943. You're sitting in a cramped office in London, surrounded by papers covered in neat rows of numbers. Outside, air raid sirens wail their familiar song of terror. But you're not running for shelter. You're calculating how many people should die tonight. Your job title is Operations Research Analyst, which sounds clean and academic. What you actually do is figure out the most efficient way to kill strangers you'll never meet. And your favorite tool? A mathematical curve so beautiful, so perfectly symmetrical that it's taught in every statistics class around the world. You can probably see it in your mind right now, that gentle hill shape, rising smoothly from nothing, peaking in the middle, then descending just as gracefully back to nothing. It looks like a sleeping cat's back. Or maybe a perfectly formed sand dune. Mathematicians call it the Gaussian distribution. Most people know it as the bell curve. Tonight, this elegant piece of mathematics will help you decide that killing 30,000 civilians is acceptable. But 35,000, that might be pushing it. You might be wondering how we got here, how something as abstract as a mathematical formula ended up with blood on its hands, how the same equation used to grade test scores and measure heights somehow became the architect of mass destruction. The answer is simpler and more terrifying than you might think. Math doesn't just describe our world. Sometimes it reshapes it entirely. And when brilliant minds take beautiful equations and hand them to people with ugly intentions, the results can be catastrophic. This isn't just another story about World War II. It's about the moment when mathematics stopped being innocent, when numbers became weapons, when a curve that should have remained safely tucked away in textbooks instead became the blueprint for some of humanity's darkest hours. So, settle in, because we're about to explore how an equation discovered by a German genius in 1809 became the mathematical foundation for strategic bombing campaigns that would incinerate entire cities, how statisticians in suits and ties calculated death tolls like grocery lists, how the bell curve became a killing curve. And yes, you're going to understand the math, even if numbers usually make your brain hurt, because this story isn't really about mathematics. It's about what happens when we use math to make the unthinkable feel routine. Let's start with something you already know, even if you don't realize it. You've been living inside the bell curve your entire life. Your height? It falls somewhere on a bell curve. Your intelligence test scores back in school? Bell curve. The time it takes you to get to work each morning? You guessed it. Even the number of typos in this script probably follows that same gentle, sloping pattern. The bell curve is everywhere because it describes how nature distributes almost everything. Think of it like this. Imagine you're throwing darts at a dartboard, but you're blindfolded and slightly drunk. Most of your darts will cluster around the center, some will scatter to the sides, and a few unlucky throws will end up in the wall behind you. Plot those dart positions on a graph, and you'll get that familiar hill shape. Carl Friedrich Gauss figured this out in 1809, and it made him famous among people who get excited about mathematical equations. Gauss was the kind of genius who solved mathematical problems in his head, while other people were still trying to understand the question. He discovered this distribution while studying astronomical observations, trying to figure out why measurements of the same star's position kept varying slightly. Here's what made Gauss's curve so seductive to the mathematical mind. It was predictable. Beautifully, reassuringly predictable. You could look at any bell curve and know exactly what it would tell you. About 68% of everything falls within one standard deviation of the average. About 95% falls within 2 standard deviations, and 99.7% falls within 3. These weren't just numbers, they were promises, mathematical certainties in an uncertain world. Think of it like a recipe that works every single time. Whether you're measuring the wingspan of butterflies or the test scores of 10,000 students, the bell curve would appear like clockwork. It was nature's signature, written in the language of statistics. But here's where things get interesting and a little unsettling. The bell curve didn't just describe things that already existed. It started predicting things that hadn't happened yet. If you knew enough about a system, any system, you could use the curve to forecast the future with startling accuracy. Insurance companies fell in love with it first. They realized they could predict with mathematical precision how many of their customers would die in any given year. Not which specific customers, of course, but the total number. It was like having a crystal ball, except this one was powered by arithmetic instead of magic. The military noticed. And when the military notices a mathematical tool that can predict outcomes with scientific precision, that tool doesn't stay innocent for very long. By the 1940s, a new breed of military thinker had emerged. They called themselves operations researchers, and they approached warfare like engineers approaching a construction project. Every problem had an optimal solution. Every decision could be calculated, measured, and optimized. These weren't bloodthirsty generals dreaming of conquest. They were academics with slide rules and calculating machines, professors who'd been pulled from university campuses and given uniforms. Their job was to make war more efficient, more scientific, more rational. And they had fallen completely in love with the bell curve. Here's why. War, they realized, was just another system that could be measured and predicted. Bomb accuracy followed a bell curve. Most bombs hit near their targets, some scattered wider, a few went wildly off course. Pilot performance followed a bell curve. Even enemy response times followed predictable patterns that could be mapped onto that familiar hill shape. If you could measure it, you could model it. If you could model it, you could optimize it. And if you could optimize it, you could win wars more efficiently than anyone had ever imagined. The bell curve promised to turn the chaos of combat into something manageable, something controllable. It offered the intoxicating possibility that warfare could be reduced to a series of mathematical equations solved with the same precision used to calculate planetary orbits. But there was a problem with this approach. Actually, there were several problems, but the biggest one was this. The bell curve doesn't distinguish between acceptable and unacceptable outcomes. It just tells you what's statistically likely to happen. When you're measuring test scores, that's fine. Nobody loses sleep over whether a C+ is morally superior to a B-. But when you're measuring casualty rates, when you're calculating how many civilians will die in a bombing raid, the mathematical beauty of the curve starts to feel a lot less beautiful. The operations researchers had a solution for this moral discomfort. They called it acceptable loss parameters. Sounds clinical, doesn't it? Professional, scientific. What it actually meant was this. They would use the bell curve to calculate how many people would probably die in any given military operation. Then they would decide, using more mathematics of course, whether that number fell within acceptable limits. The curve would tell them that bombing a particular target had an 85% chance of killing between 5,000 and 8,000 civilians. The mathematics was clear, precise, and utterly confident. Whether those deaths were acceptable became just another calculation, another optimization problem to solve. And this is where Carl Friedrich Gauss's beautiful, innocent mathematical discovery began its transformation into something else entirely. Something that would help justify some of the most devastating bombing campaigns in human history. The mathematicians had found a way to make mass death feel routine, scientific, inevitable. They had weaponized certainty itself. Picture yourself walking into a conference room in 1942. The walls are covered with maps of Europe, pins marking targets like a deadly game of darts. Around a polished oak table sit men in pressed uniforms and perfectly knotted ties, smoking cigarettes and discussing murder with the casual tone usually reserved for quarterly sales reports. These are the architects of strategic bombing, and they have a problem that keeps them awake at night. The problem isn't moral squeamishness about killing civilians. That ship sailed long ago. The problem is efficiency. How do you maximize destruction while minimizing cost? How do you kill the most people with the fewest resources? How do you turn warfare into a science? Enter the operations researchers clutching their bell curves like holy scripture. They had spent months studying bombing patterns, measuring blast radii, calculating casualty rates with the methodical precision of accountants auditing a small business. And they had discovered something beautiful. Death, it turned out, was surprisingly predictable. Drop a bomb on a residential neighborhood, and the casualties would spread out in a pattern that mapped almost perfectly onto their beloved bell curve. Most deaths occurred at the center of the blast. Fewer deaths happened at moderate distances. The unlucky few at the outer edges might survive with injuries or escape entirely. It was like measuring rainfall, except instead of water, they were measuring human obliteration. The mathematicians had cracked the code of mass killing. They could predict, with stunning accuracy, how many people would die based on bomb tonnage, blast radius, population density, and building construction. Feed these variables into their equations, and out popped a number. Clean, precise, scientifically valid. But here's what made this truly diabolical. The bell curve didn't just predict casualties, it justified them. Think about how this worked in practice. A general would propose bombing a German industrial target. The operations researchers would plug the numbers into their formulas. The curve would spit out its prediction, 12,000 civilian deaths plus or minus 2,000 with 95% confidence. Then came the crucial question, was 12,000 acceptable? The bell curve made this question feel answerable, scientific, rational. The mathematicians had transformed a moral horror into a statistical optimization problem. They had turned mass murder into a multiple-choice question with a mathematically correct answer. The most chilling part, they genuinely believed they were making warfare more humane. Here's their logic. Twisted as it sounds, if you could calculate casualties in advance, you could minimize them. Plan more precisely. Avoid unnecessary deaths. The bell curve wasn't just predicting carnage, it was preventing it. Robert McNamara, who would later become Defense Secretary during Vietnam, was one of these statistical warriors. During World War II, he applied bell curve analysis to bombing campaigns over Japan with the enthusiasm of a graduate student working on his thesis. McNamara and his team calculated that firebombing Tokyo would kill approximately 100,000 people. The curve told them so, with mathematical certainty. They ran the numbers multiple times, adjusting for wind patterns, building materials, population density. The mathematics kept giving them the same answer. So, they did it. On March 9, 1945, American B-29s dropped incendiary bombs on Tokyo, in a pattern carefully designed to maximize the efficiency of mass killing. The fires spread exactly as the equations predicted. The death toll landed almost precisely where the bell curve said it would. From a mathematical perspective, it was a stunning success. The models had worked perfectly. The predictions proved accurate. The optimization was complete. From a human perspective, it was one of the deadliest single nights in human history. The operations researchers celebrated. Their equations had performed flawlessly. The bell curve had proven its worth as a tool of warfare. They had successfully reduced the incineration of 100,000 human beings to a statistical validation exercise. But Tokyo was just the beginning. The mathematical approach to mass killing was spreading through military planning, like a virus of rational thought. Dresden became another test case. The bell curve predicted that bombing the city centre during carnival season would maximize civilian casualties while minimizing military value. The mathematics were clear. Maximum disruption for minimum resource expenditure. The bombers came in waves, just as the equation suggested. First conventional explosives to break open buildings, then incendiaries to start fires. The second wave targeted rescue operations, because the curve predicted that's when survivors would be most densely concentrated. 25,000 people died, almost exactly as predicted. Another mathematical triumph. Another human catastrophe reduced to statistical accuracy. The most disturbing part wasn't the killing itself. Humans have been slaughtering each other for millennia. The disturbing part was how the mathematics made it feel inevitable. Scientific, morally neutral. The bell curve had become a permission slip for atrocity. As long as the casualties fell within predicted parameters, as long as the death toll matched the statistical models, the killing could continue with mathematical blessing. The operations researchers had solved the ancient problem of warfare, how to commit mass murder without feeling like murderers. They had found a way to delegate moral responsibility to mathematics itself. If the curve predicted 15,000 deaths and 15,000 people died, then nobody was to blame. The mathematics had simply fulfilled its promise. Nature had taken its statistically inevitable course. This wasn't evil genius at work. It was something far more dangerous, brilliant people using brilliant tools to avoid thinking about what they were actually doing. Let me tell you about Miyoko Matsubara. She was 8 years old on March 9th, 1945, living in Tokyo with her grandmother, while her parents worked in a munitions factory outside the city. Miyoko doesn't appear in any of the mathematical models. She's not a data point on the bell curve. She's what statisticians call an outlier, someone whose individual story gets lost in the beautiful symmetry of aggregate data. But Miyoko's story is where the mathematics finally meets reality, where the elegant curves smash headfirst into burning flesh and screaming children. The operations researchers had calculated that the firebombing would create optimal casualties through a combination of high explosives followed by incendiaries. They had mapped out fire spread patterns, wind velocities, escape route bottlenecks. Their models predicted that residential areas would burn in concentric circles, with casualty rates following their beloved bell curve distribution. What their equations didn't capture was the sound Miyoko heard when the first bombs fell. Like thunder, but wrong somehow. Too close. Too angry. The mathematical models had accounted for building materials, mostly wood and paper, highly flammable, optimal for incendiary effectiveness. They had calculated burn rates, structural collapse probabilities, and population density per square kilometre. What they couldn't calculate was the way Miyoko's grandmother grabbed her hand and pulled her toward the door, only to find that the street outside had become a river of liquid fire. The bell curve had predicted this, of course. Fire spread follows predictable patterns. Wind carries flames in mathematically modelable directions. The equations had accounted for everything: fuel load, oxygen availability, thermal dynamics. Everything except what it feels like to watch your grandmother burn alive while you hide under a bridge, breathing smoke so thick it turns day into night. The operations researchers had run sensitivity analyses on their casualty predictions. They had confidence intervals and margin of error calculations. They knew, with 95% statistical certainty, that between 90,000 and 110,000 people would die that night. Miyoko became number 97,543 in their final count, a data point that proved their models worked exactly as designed. But here's what the mathematics missed. Miyoko didn't die from the bombs. She didn't die from the fires. She died 3 weeks later in a refugee camp, from infected burns and malnutrition, clutching a doll made from scraps of her grandmother's kimono. The bell curve doesn't have a category for delayed deaths caused by mathematical precision. Let's travel to Dresden, February 13th, 1945. The operations researchers had identified carnival season as optimal timing for maximum civilian casualties. Their models showed that holiday celebrations would concentrate population in the city centre, increasing the efficiency of area bombing. Kurt Vonnegut was there, a prisoner of war working in a slaughterhouse. He would later write about what he saw, but even his writer's imagination struggled to capture what happens when mathematical theory becomes burning reality. The first wave of bombers arrived exactly on schedule, just as the equations predicted. High explosives to break open buildings and expose flammable materials. The timing was perfect, mathematically speaking. Optimal dispersion patterns for maximum structural damage. Vonnegut watched the sky fill with aircraft arranged in precise formations, following flight paths calculated to ensure complete target coverage with minimal resource waste. The bombing pattern had been optimized using statistical models that predicted debris scatter, fire spread, and escape route congestion. Then came the incendiaries, thousands of them, dropped in a pattern designed to create a firestorm that would be visible from space. The operations researchers had calculated the exact temperature needed to melt glass, to turn asphalt into flowing rivers, to suck oxygen from underground shelters with mathematical precision. The firestorm reached 1,500 degrees Celsius, exactly as the thermal dynamics equations predicted. It created winds of 150 miles per hour, precisely matching the meteorological models. It consumed everything within a 2.5 square mile radius, just as the burn rate calculations had forecast. From a mathematical perspective, Dresden was a masterpiece of applied statistics. Every prediction proved accurate, every calculation validated. The bell curve had performed flawlessly. From a human perspective, it was hell made manifest by slide rule and calculating machine. Vonnegut survived by hiding in an underground meat locker, breathing through wet rags while the city above him melted into statistical perfection. When he emerged 3 days later, Dresden looked like the surface of the moon, if the moon were made of ash and human bone. 25,000 people had died, almost exactly matching the operations researchers' predictions. Another triumph of mathematical modelling, another validation of the bell curve's deadly accuracy. But here's what haunted Vonnegut for the rest of his life: the mathematical precision of it all, the way human suffering had been reduced to optimal burn patterns and casualty distribution curves, the way mass murder had been transformed into a successful science experiment. The operations researchers never met Miyoko or Vonnegut. They never saw the faces behind their statistics. They worked with clean numbers on white paper, calculating death tolls with the same detached precision used to balance checkbooks. This was the true horror of mathematical warfare. It made mass killing feel routine, administrative, morally neutral. The bell curve had created a buffer between cause and effect, between decision and consequence. The mathematicians could optimize casualty rates without ever seeing a casualty. They could calculate the most efficient ways to kill strangers they would never meet, in cities they would never visit, for reasons that felt both utterly rational and completely insane. They had solved the ancient problem of warfare, how to commit atrocities without feeling like monsters. They had found a way to delegate moral responsibility to mathematics itself. The curve made them do it. August 15th, 1945, Japan surrenders. The war is over. In offices across America and Britain, operations researchers are packing up their calculating machines and slide rules, preparing to return to their university posts. They're proud of their work. The mathematics had performed flawlessly. The bell curve had proven its worth as a tool of warfare. They had helped win the war through superior statistical analysis. History would remember them as innovators, pioneers of scientific warfare. They had transformed military strategy from gut instinct into precise mathematical science. But something strange happened in the months that followed, something the equations hadn't predicted. The photographs came back first, images from Dresden, Tokyo, Hamburg, cities that looked like they had been erased with a giant eraser, leaving only smudges where neighborhoods used to exist. The mathematical precision was visible in the burn patterns, the perfectly circular zones of destruction, the statistical accuracy of the devastation. Then came the survivor accounts. Stories like Miyoko's multiplied by thousands, human faces attached to the data points, individual tragedies hidden within the aggregate statistics. Robert McNamara, the statistical warrior who had helped optimize the Tokyo firebombing, started having nightmares. He would later admit that if America had lost the war, he would have been tried as a war criminal. The mathematics that once felt so clean and rational suddenly seemed covered in blood. Here's what the operations researchers discovered in the aftermath. The bell curve doesn't have a conscience. It predicts outcomes with perfect mathematical accuracy, but it can't tell you whether those outcomes are morally acceptable. It can calculate casualty rates with scientific precision, but it can't distinguish between necessary deaths and gratuitous slaughter. The curve had worked exactly as designed. The problem was the design itself. Curtis LeMay, the Air Force general who oversaw many of the bombing campaigns, put it with characteristic bluntness. I suppose if I had lost the war, I would have been tried as a war criminal. The mathematics had made it feel inevitable, but inevitability and morality aren't the same thing. Some of the operations researchers tried to rationalize their work. They argued that mathematical bombing had actually saved lives by shortening the war. They claimed that precise calculations had minimized unnecessary casualties. They insisted that scientific warfare was more humane than the alternative. Others weren't so sure. They had created tools that made mass killing feel routine, administrative, morally neutral. They had found ways to calculate acceptable death tolls like quarterly sales targets. They had reduced human suffering to statistical optimization problems. The bell curve itself remained innocent, of course. Mathematical formulas don't have moral agency. They simply describe patterns in data, predict likely outcomes, quantify uncertainty. Gaussian distributions don't kill people any more than kitchen knives commit murder. But the combination of mathematical precision and human moral flexibility had proven devastatingly effective. The curve had provided a veneer of scientific respectability to decisions that would have been unthinkable without statistical backing. The legacy of mathematical warfare didn't end with World War II. If anything, it was just getting started. During the Vietnam War, McNamara brought his bell curve obsession to the Pentagon as Secretary of Defense. He demanded statistical measurements for everything: body counts, kill ratios, progress indicators. The war became an exercise in applied mathematics, with success measured in spreadsheets rather than strategic objectives. The military developed something called the Hamlet Evaluation System, which used mathematical models to calculate pacification progress in Vietnamese villages. They assigned numerical scores to civilian loyalty, insurgent activity, and government control. The bell curve told them they were winning, even as the war spiraled into disaster. McNamara's whiz kids, young analysts armed with computers and statistical models, treated Vietnam like a massive optimization problem. They calculated bombing tonnages, predicted casualty rates, and measured success through mathematical metrics that bore little resemblance to reality on the ground. The mathematics kept telling them they were winning right up until Saigon fell. Today, the descendants of those World War II operations researchers work in places with names like RAND Corporation, Strategic Air Command, and the Pentagon's Office of Net Assessment. They use computers instead of slide rules, sophisticated algorithms instead of simple bell curves, but the fundamental approach remains the same. Modern warfare is still shaped by mathematical models that calculate acceptable casualty rates, predict optimal bombing patterns, and quantify the efficiency of mass killing. Drone strikes are planned using statistical algorithms that weigh civilian casualties against military objectives. The mathematics have become more sophisticated, but the moral calculus remains unchanged. The bell curve appears in targeting software that helps missile guidance systems calculate blast radii and casualty probabilities. It shapes the algorithms that decide which buildings to destroy, which neighborhoods to evacuate, which people to classify as acceptable losses. Military planners still use Gaussian distributions to model everything from weapons accuracy to enemy response times. The curve that Carl Friedrich Gauss discovered while studying star positions continues to influence decisions about who lives and who dies in conflicts around the world. But here's what's changed since 1945. We can no longer pretend that mathematics is morally neutral. We've learned that statistical models don't just describe reality, they shape it. When you reduce human lives to data points on a curve, you make it easier to erase those lives with mathematical precision. The operations researchers of World War II thought they were making warfare more scientific, more rational, more humane. Instead, they created tools that made mass killing feel routine. They found ways to commit atrocities while maintaining the illusion of moral respectability. They discovered that the most dangerous weapon isn't a bomb or a bullet. It's a mathematical formula that makes horror feel inevitable. The bell curve didn't kill 100,000 people. People killed 100,000 people. But the curve made it easier to sleep at night afterward. It transformed mass murder into a statistical validation exercise. It turned moral choices into optimization problems. It made the unthinkable feel routine, scientific, mathematically justified. Carl Friedrich Gauss died in 1855, long before his beautiful mathematical discovery was weaponized for mass destruction. He never could have imagined that his elegant curve would someday help justify the incineration of entire cities. But that's the thing about mathematics. It's a tool, nothing more. A knife can spread butter or commit murder. A bell curve can describe test scores or calculate casualty rates. The mathematics itself remains morally neutral. The people who wield it, however, are not. And that might be the most disturbing lesson of all. We don't need evil geniuses to commit atrocities. We just need brilliant people with beautiful tools who stop thinking about what they're actually doing. The curve is still out there, still predicting, still optimizing, still making the unthinkable feel mathematically inevitable. Still waiting for the next group of smart people to forget that numbers on a page represent human lives. Still ready to kill again, with perfect statistical precision,